building on what we did on Monday. So on Monday, I introduced you to the basic circuit symbol of an operational amplifier and what you would get if you did not have negative feedback and you wired up some voltages on the inputs. And also we had a quick look at what happens when you put negative feedback into, well, what happens when you connect the output of your op amp back into the inverting terminal or the negative terminal of the op amp. Okay, so today we're going to use that property of negative feedback to show you how we practically use op amps to do what we set out to do, which was to amplify signals. Okay, so but first, let's start off with a really bad op amp joke. Can anyone have a guess as to why do inverting op amps make the harshest critics? Something about the wrong way, sorry, what was that? They take everything the wrong way, that's a good answer. Any others? It's because they only give negative feedback. Ha 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 ha. I've got a little bit I thought that was cute, so I put that on there, and that's probably most of your reactions. Yeah. So negative feedback, and it's actually not technically correct anyway, so that's what adds to the badness of the joke. Anyway, so what are we doing today? So by the end of today, I want you to be able to observe and recall that when you add a few passive components around an op amp, so what key thing here is a few passive components. What is the main passive component you've been using? Resistor, good. So you can add a few resistors around an op amp and it allows you to program its output so that the exact performance of the op amp doesn't matter. Now before we had this parameter AOL, right? And I said that was about 100,000 or 10,000, some big number. Now, in reality, that number is really poorly controlled. So you buy an op amp off the shelf, you're not going to get AOL to be exactly 100,000. And it will vary depending on the kinds of signals you put into it. So it's not really good to build hardware or build a circuit using unreliable components. What negative feedback allows us to do is to be able to use these op amps in such a way that we don't really need this AOL to be a perfect number. We just need it to be big. Okay, that's the key takeaway message. We want you to be able to recall different configurations of some basic op amp circuits. So I'll go through 2 or 3 of these basic op amp circuits, and they will allow you to do the basic thing that we want op amps to be able to do, which is to amplify a signal. So remember I said you get small signals, they travel a distance, they get smaller and smaller. If I want to be able to have that signal used somewhere far away, I need to amplify it. So we'll actually show you how to construct these op amp circuits now. And finally, we want you to be able to, after today, to be able to analyze some simple op amp circuits. So by analyze, I mean I give you a circuit with some resistors in there, and I want you to be able to tell me what the relationship between the output is to the input. Simple as that. How much bigger is the output than the input signal given I give you this op amp configuration? Okay, so first thing that we need to define is something called gain. Okay, as the name suggests, it usually means something. It means making something bigger. You're gaining energy, for instance. And this is one of the most common quantities for any op amp configuration to be calculated. Now, gain, really, when you're talking about gain, you're talking about some relationship between output to input. Sometimes you may have multiple inputs. So let's say you've got an audio mixer. You might put in someone's voice on one channel and the backing track on another channel, and that would be 2 input signals. You could put them through an op amp and mix them together to give one output signal. That's not strictly gain, if you will, but We talk about gain really as the relationship between the output to the input. Now, the key thing here is that gain may be positive or negative. If a gain is negative, then this implies that the output is simply inverted relative to the input. So if my input is like this, if I have a positive gain, maybe I can change my color here. So a positive gain would say, so if this is the input, the output would be something like this. That would be a positive gain. So the output signal is some amount larger than the input signal. And at the same time, it's possible to have negative gain. And negative gain would look something like this. So the signal is increased in amplitude, but it goes in the opposite voltage direction. Okay, so that's the first key thing to realize about gain. It can be negative or positive. Okay, let's change this back to red. Okay, so to do everything that we're going to do today, we build directly on what we learnt on Monday, which, if you remember nothing else, you needed to remember these two things, which are the two golden rules. When we have an op amp that's put together in a negative feedback configuration, the voltages, well, the op amp will try to make the voltages at the two terminals, the inverting and the non-inverting terminals. So this would be V minus, this would be V plus. It's trying to make those two voltages the same. So remember, all that circuitry inside the op amp is reconfiguring itself, doing smart things so that this condition holds true. Okay, so, and this is only true in negative feedback. Okay, so that's where you've got some path from V out all the way back to the negative terminal. So that's the first thing. Commit that to memory. The second thing is that when we're talking about an ideal op amp, no current flows into or out of these two terminals. Okay, so that's I minus. Apologies for the scribble. And that's the second assumption. Okay, and these arise because of when we assumed that there was a resistor in here, and we assumed that that resistor had infinite resistance. So that means no current flowed. Okay, in reality, not quite true, but in analysis, we can take it as true for ENG1030 anyway. Okay, so with those in mind, this is the circuit that I showed you that we just connected the output directly back into the negative terminal. And there's another name for this, so it's a very common circuit. It's called a unity gain buffer. So take those three words. You might know what unity means, you might know what gain means, you might know what buffer means. Cram them all together, it means something totally different. That's what tends to happen in engineering. But in this case, a unity gain buffer is this exact circuit where you've got an op amp with the output connected to the connected to the inverting terminal via a wire, so there's no resistors in the way. And in this case, we showed, I glossed over the we showed bit, but if you're interested, you can look back and see that this is the case via some intuitive logic, that V plus was equal to V minus, and if that's the case, then in this case you've got over here V out being equal to V minus because the voltages here are, well, the two nodes here are connected directly by a wire, right? And over here, just by looking at the definition here, Vs is equal to V plus, okay, logical. And because we know this condition, V plus equals V minus, because we have negative feedback, hence V out must be equal to Vs. Okay, so are we now, knowing these two simple calculations, we can work out the factor, G, which is the gain for this op amp circuit. So in here, if you've got V out equals Vs, then the gain, which is the ratio between the output, V out, and the input Vs, is just equal to 1, right? Because V out equals Vs, so therefore V out over Vs is equal to 1. And that's pretty much the same logic that you take when you analyze any op amp circuit. So you look at the output, you look at the input, and you try to relate the output to the input via this. If the circuit is in negative feedback, you relate it somehow via the fact that these two things are equal. Okay, so now that's the simplest case. Now, just a little bit more background on this. Why is this called a unity gain buffer? Well, it's got unity gain, because the gain is 1. And it's called a buffer because there is a disconnect between the actual circuit which connects to this side, which is Vs, and the circuit that connects to this side, which is V out. There's an op amp in between the two stages. So this could be stage 2, this could be stage 1. Those two parts of the circuit are not actually connected, so there is a buffer in between them, and that's why it's called a unity gain buffer. Yep, question?
What's the point of having an op amp in negative feedback?
Sorry?
What's the point?
Of having the op amp in negative feedback? Yeah. Yep, that's a very good question. So the point will be covered, I will get to the finer details of why we have this next week. Yep, but first I want to introduce you to this so that you can do stuff with it straight away, especially in your labs, because next week your labs will have op amps in it. So you can do stuff with it straight away, do calculations with it, produce circuits which produce gain, and then I will bore you with the details of why this negative feedback is useful. Okay? Are we okay with that? Or does anyone want to know those details now? One person, okay. 2 people. All right, 3 people. 4, okay, you're still a minority. You've been voted down by democracy, which I don't subscribe to, but that's the way. If you want to know, come after the lecture, because the lecture today, we'll have a little bit of time at the end. Come down and I can explain it to you. Okay? Very quickly, but we'll go into that in detail. Okay, so the purpose of the unity gain buffer is so you say, oh, great, so the input's the same as the output, why don't we just connect it via a wire? Logical question. What it does is it does something important. It decouples the circuits on the input and output. And this is useful because this will stop signals from traveling in the wrong direction in your circuit. So in this case, let's say you have an audio mixer, and you have one of these on each of the audio channels. So you've got voice coming in one, and then you've got another unity gain buffer, you've got background music on, backing track on the other. Then you don't get unwanted electrical signals passing from one way to the other because this op amp will block those. Okay? Another one is that this op amp can provide a really large current gain. So over here, you may have signals which are really tiny signals. They may come from sensors such as you might have a photosensor which detects light, and they produce really small amounts of current. But I want to be able to amplify that signal, but I can't draw lots of current from that particular sensor. So what the op amp does is it takes that signal and gives you a whole lot of current out so that you can work with that. Okay, so just something to recall why this is the case, why this unity gain buffer works, and is because that input resistance seen by those circuits connected is infinite. So over here, well, sorry. Okay, so remember inside here, there was this infinity. We're saying that Ri equals infinity. So this is plus, minus, V plus, V minus. And the output resistance here was seen as almost 0. Okay. This is the case for the ideal op amp, and this really becomes quite important later on because the unity gain buffer allows you to connect multiple stages of circuitry together. And there are considerations that you need to, well, considerations you haven't come across, but you will come across when you design slightly more complex circuits. Okay. Did Jamie go through a slide like this in his, when he was talking about current and voltage and doing calculations? Yes? No? Okay. So the reason this is in here is because, and this will help you when you go back to more complicated circuit analysis, when Jamie gets back to do those bits. Here's a shortcut for helping you to define a current going through a particular resistor with voltages on either end of the resistor. Okay, so over here, if I just look at the stuff in green, this is useful because from now on, you want to be working with currents and voltages in this manner. It just makes things a whole world easier when we're doing calculations. So if I've got a resistor and it's got a voltage on either side, V1, V2, if I want to calculate the current going to the right, I just take the source node where the current's coming from, V1, subtract V2, the voltage on either side, and divide it by the resistor. If I want to calculate the current the other way, I take V2, subtract V1, and divide it by the resistor. Okay, so that's the quick, easy method of figuring out what the current is through this resistor. You don't need to find that, well, you're essentially finding the voltage across the resistor. So it might be something like this, V, but by going from the source voltage to the destination voltage of the arrow, it gives you the positive current in that direction. Okay, so that's just a quick thing which now leads me to this. Okay, so here is what we call the first useful type of amplifier that you have. Sorry, that's not true. Unity gain buffer is very useful. The second useful amplifier that we have, which is called the non-inverting amplifier. Okay, so this will be a typical thing that you would ask to do. Determine the gain for this circuit, and in this case we haven't put any numbers in because that would distract from the concepts. We're just working with the algebraic values of resistance and voltage. So determine the gain G equals V out over Vs for this circuit. So you've got V out here, and you've got Vs. So once you find this G, you can easily calculate what the voltage on the output is for any particular voltage on the input. Okay? So how do we go about doing this? Now this method that I'm showing you now works pretty much for any op amp. So even really complex op amps that you may get later, refer back to this methodology. Okay, so firstly, you must check, is this circuit in negative feedback? So is this circuit in negative feedback? Yes. Why is it in negative feedback? Why is it in negative feedback? So there is a path from the output through R2, through this piece of wire, back to this negative terminal, right? So yes, this is in negative feedback. Never mind this resistor here. Because there is a path that gets back from the output to the negative input, this is in negative feedback. Straight away, that allows you to use this rule, okay? It allows you to use V plus equals V minus. If this were not the case, you cannot use this, okay? And we should see that if you can't use this, it makes analysis a whole lot more tricky. But we have negative feedback, so we can use this rule. Now, if I want to find the relationship between V out and Vs, then a good way to do this is to relate V out to the quantity V minus, use the fact that V plus equals V minus, and relate V plus back to Vs. Okay, so which is exactly what we did for the unity gain buffer, but now we're just adding a couple of resistors in here, and we'll see how this pans out. Okay, so now, putting together some concepts you learned in the first couple of weeks. Kirchhoff's current law. Remember that? It says that all the currents coming out of any node must sum to 0. Okay? So in this case, I've drawn all the currents coming out of this node here. I1, I minus, and I2. And I'm saying, via Kirchhoff's current law, that the sum of all these currents must be equal to 0. You could work it the other way around. You could say all the currents coming in. I've just purely chosen to say all the currents coming out because that's the way I like to do it. You don't have to do it that way. The results will be the same. So if KCL at this node V minus So this is one bit which can make people go, huh? This is V minus, yes, but also this is V minus because it's connected directly to the wire, right? Okay, so when I'm referring to, I'm talking about here, not here. Just makes things a little bit easier. So now substitute the current through each of these directions by the quantities that we know. So we don't know what these currents are, but we can relate those currents to the voltages and the resistors that we have in the circuit, right? So we've got V out, you've got R1 and R2, and you've got this current going to the left, which, because we are assuming that this circuit uses an ideal op amp, we know that this current here must be 0, right? That's the second really important thing. So the first important thing was that these two are equal. The second important thing is there's no current coming into this op amp. Now this makes things really, really, really easy because now you see why I had to show you the rule before about how to calculate currents from voltages. Well, this one goes to here, and this one goes to here. Well, I1 is just, okay, so I1 is V minus, subtract 0, so here's 0 volts because it's connected to ground, divided by R1, right? That's what we've got here. That's I1. I2 is V minus, subtract, so I2 here is going upwards, so I2 is V minus, subtract V out, divided by R2. Can we all see that? And so, and because this is equal to 0, we say plus 0, which is I minus, must sum to 0 by Kirchhoff's current law. Okay, so easy enough. Let's collect up the terms. So you factorize out V minus, take V out to the other side of the equation. You've got something like that. And then let's do a little bit of algebra. Oh, I love that. I say it's simple algebra, and then you get to it and you go, oh, I've got to remember algebra. But it is simple algebra. So V out over V minus equals 1 over R2 plus R1. And finally, we use this fact here that Vs equals V plus equals V minus, right? To get the overall gain expression for this type of amplifier, which is 1 plus R2 over R1. Okay, so what are the consequences of this? Well, there's a reason this thing is called a non-inverting amplifier, and that's because what is the gain, what is the restriction on the gain of this amplifier? It'll always be equal to or greater than 1, right? Because R2 and R1 are only positive numbers. We don't have negative resistors. Okay? Not in the realms that we work in. And because these are both positive, this will always be greater than 1. And the gain will always be greater than 1. Always positive. So therefore, it's a non-inverting amplifier. Simple enough? So now, if I want to design, I turn the question around and I say, design me an amplifier that gives me a gain G of 10, say. What do I need to do? Well, I need to know that I can use this configuration, and I need to select values for resistor 1 and resistor 2 that give me a total of 10. So I could make R2 equals 9, R1 equals 1, and I would mathematically here get gain equals 10. Now you don't believe me, you think this is all mathematical hocus pocus. Just take your op amp into the lab, put up this circuit, play around with values of resistors, use your scope to see, use your oscilloscope to see what values you get on the output compared to the input values that you put in. Okay? All right, so here's another example. So here we have, so here's another non-inverting ampere example. So here, as we said, the gain was this given by this equation, 1 plus R2 over R1. And as I said, it's entirely set by the two resistors. So if I have an input of 1 volt and it's a sinusoidal input, then if I take R2 equals 9 kilo ohms and R1 equals 1 kilo ohm, by this calculation we should see that the gain is 10, right? And so if I look at the red, the output should be, well, it will be a sine wave which goes in the same direction as the input sine wave and is scaled by a factor of 10. Okay? That's great, you say. Now, I've also included here the supply voltages. So we've ignored those for a second, but they do play an important part because in this example that I've just put up, we're saying that the supply voltages are 15 volts and negative 15 volts. So everything's okay because the output only goes up to 10 and minus 10. What if the supply voltage was 6 and negative 6? What would happen then? So the circuit, remembering what we did on Monday, the circuit would experience clipping. Okay? And the output will be clipped at the supply values because the output can't be greater than 6 volts or smaller than negative 6 volts. Okay? Because these are the supply voltages, and the op amp cannot supply voltage greater than or less than these limits. Okay? So this is what the output waveform would look like. You would have, so this would be 6 volts, and this would be negative 6 volts. And I pretty much guarantee some of you will see this when you do your lab. Okay? And then you'll go, what's going on? And then you'll go, John told me in the lecture that there's something called clipping. Okay? All right. So let's take a little bit of a breather and have a go at this melts question. Yep, question?
Does the VS over there represent input voltage? Or does that represent...
You mean on this?
Yeah.
The VS, yes, the VS here is the input voltage.
So that doesn't represent the supply voltage?
No, VS plus and VS minus represent the supply. Yep, that's right. All right, so have a go at this. I'll open up the melts question. So take some time. Really try to digest what you saw in that first example to work out the second example. So doing a gain for this. And unlocked. All right. All right, let's have a go at this one. So please turn to your neighbours, discuss this. 2 heads are better than 1, 3 heads are better than 2. So I'll give you a little bit of time for this because it's a bit more involved than your run-of-the-mill calculation. Okay, so remember what I said about the way you do these things? You firstly check, is the circuit in negative feedback? If so, what does that mean? Then go about relating VS and V out via the intermediate value of B plus and B minus. And this will almost always involve using a Kirchhoff's current law equation at some node in the circuit. Oh, and it will always involve a bit of algebra. Has anyone looked at the leaderboard at all? I noticed it's thinning out a bit at the top. It's interesting. I noticed there were some interesting aliases, interesting nicknames. Had to adjust some of them accordingly. We do know actually who you are, so we can check that. Okay, so anyone need more time? Yes. All right, more time, good. All right, one more minute. We'll go to 3:44 on that clock. Okay, if you haven't put something in, just put anything in, randomly put something in. Oh, yeah, yeah. Oh, we get a few counts here, yeah. All right, so last chance. All right, closed. Okay, so what do we got? Okay, so if you're playing Who Wants to Be a Millionaire, do you go with the ask the crowd? All right, so most answers. Oh yeah, what's the understanding like? Okay, most people think they understand. All right, so the answer is in fact, well, we'll work it out. Okay, so what do we do here? So the answer comes from, okay, so what are the two facts we know? Is it in neg feedback? Yes. Therefore, V plus equals V minus. Good. Then you've got, well, there's really only one interesting node here, right? This one. So you've got I1, I2, I minus, and we know that I minus is equal to 0. So therefore, KCL says I1 plus I2 plus I minus equals 0. And we substitute for the i's. So I1 is V minus subtract V out over R2 plus I2, which is V minus subtract Vs over R1 plus 0 equals 0. We also know that V plus equals V minus, which is equal to what? 0. Good, because it's connected to ground here. 0 volts here means this is 0 volts. Incidentally, this thing here is now called a virtual earth because it's at the same voltage as ground, but it is not actually connected to ground. So that's why it's called a virtual earth. Okay, so therefore, if V minus equals 0, then you've got these equal to 0. And now you've simply got minus V out over R2 equals Vs over R1. Now if I rearrange that, I get V out over Vs equals negative R2 over R1. So the answer is, in fact, D. So well done. Now if you didn't get that, I suspect that you probably just had a bit of a algebraic error for C. If you picked B, then I'm guessing, well, maybe slight adjustment of concept in your mind. If you need a bit more help, come see me. Okay. Does anyone have problems getting to the 8 a.m. lectures? Yeah, if this alarm clock is for you, right? So this, I just found this the other day, thought it might be relevant and interesting. Building an alarm clock which shocks you when you try to turn it off. Or press sleep, there's no sleeping. So you either have the music playing and waking you up, or you just have to sleep, so you grin and bear it and take an electric shock when you hit the sleep button. Can I interest anyone in buying this? Yeah? Okay. We'll order a few. Okay, so that in fact was, so this is the exact circuit that we had, and that in fact is called an inverting amplifier. And the reason that is, so here's all the working, redone. And the reason that is because, as I said, the gain of V out over Vs overall is equal to minus R2 over R1. Okay, so because R2 and R1 have to be positive, then the overall expression must always be negative, which means that if I put a signal in on here that goes in one direction, the signal on the output would go in the opposite direction. But it would be scaled by a factor of R2 and R2 over R1. Interestingly enough, you could actually have a signal being smaller than the output signal being smaller than the input signal if you made R2 smaller than R1. Okay, so what does the output look like? Well, here's R2 and R1. Well, again, in the same way, the output is directly set by those two resistors, R2 and R1. So when you design a circuit for a particular gain, you pick values of R2 and R1 which satisfy this. And if I use the same values as I did before, R2 equals 9K and R1 equals 1K, my gain will be -9, and here you can see that the output will be an inverted version and scaled by a factor of 9 of the original blue input. And just to illustrate what happens if we have clipping, anytime the voltage on the output goes bigger or smaller than the supply voltages, 6 volt and -6 volts, you get clipping. Okay? All right. So, one final. Oh, well, so I also mentioned the virtual earth. I mentioned it in quick passing because it was most relevant at that point. This is more for your reference. Over here, because you have ground at V plus, and that's equal to V minus, this point is called a virtual earth. Things about the virtual earth: no current directly flows into the earth like on a real earth, okay? And that's why it is called virtual as well. But the key thing is it makes things easier to analyze because you're not working with any more variables. You're actually getting rid of one variable, V plus and V minus, making it equal to 0. Okay, so final circuit. I'm not going to get you to analyze it. I'll analyze it for you just to show you what's going on. In this case, we haven't asked for the gain. We've asked for the voltage V out in terms of VS1 and VS2. Okay, so we want V out is equal to some function of VS1 and VS2. How would we go about doing something like that? Well, no different to how you went about solving the previous problem. So, the first thing is a circuit in negative feedback. Is there a path from output to negative terminal? Yes. You can see it through here. Okay, so that's great because it allows us to use V plus equals V minus. Hey, and guess what? V plus is equal to 0 volts because it's connected to ground. And this means V minus equals 0 volts because of this negative feedback condition. That's great because it makes things a hell of a lot simpler in terms of the algebra. Next, same method. Use Kirchhoff's current law at a relevant node. So which node do we use, I would hear you ask, if you were thinking about expanding this? Well, the choice of node you will get better at picking once you've done a few more examples. Okay? So in this case, there's only one real node which has multiple directions. That's usually a good node to pick. You'll start seeing op amps which have lots and lots of nodes and lots of directions. Picking exactly which node to do KCL on will become, it's a bit of an art which you'll get better at by practice, like anything. Okay, so KCL at this node, so I've labeled them all. So you've got I11 through this resistor, I12 through this resistor, I minus, which we all know should be 0. Okay, why? Because we're assuming this is an ideal op amp. And we've got I2 going through resistor 2. Okay, so substitute in the currents for the voltages. Okay, so I11 is the current going to the left through R11, and that'll be 0 volts. Subtract VS1 volts divided by R11. So that's this one here. I12 will be 0, again here, subtract VS2 divided by R12. And the green current here, I2 will be equal to 0 again, subtract V out. Okay, so that's the voltage on this side of this resistor, subtract the voltage on this side of the resistor, which is V out, divided by its resistance, gives us that current. Okay? All of that must sum to 0 by Kirchhoff's current law. So, we can simplify this. I've collected up V out on the left, V out on the left, and VS1 and VS2 on the right, making sure that I've kept the signs consistent. Okay? And thus, the output voltage here, the relationship between the output voltage in terms of VS1 and VS2, the two input voltages, is given by this, and I've collected the negative sign out the front because it makes it easier to show that whatever signals I've got in VS1 and VS2, they are added together by a certain weighting factor, and the weighting factor is determined by these resistors, and the output is inverted or turned upside down. And that's why this configuration is called a summing and inverting amplifier. So it adds two things and it inverts them. Okay, so there you go. Thanks very much. I will see you guys tomorrow.